Okay, so let's move on to another problem involving some um, modular addition in this case. Sorry, I'm recording this a little bit out of order. I did the multiplication problems, but I forgot to record this addition one. That's why I had to think about that. So, alright, let's just get started. The remainders when two natural numbers are divided by 16 are 11 and 14 respectively. Find the remainder when their sum is divided by 16. And find the remainder when their sum is divided by 8. So, as always, let's work with the information the problem gives us. We have two numbers, so I can call one x and one of them y. And when divided by 16, one of them has a remainder of 11. So I'm going to say x is congruent to 11 mod 16. Because whenever it says remainder, think modular. And if you're dividing by 16, you're in mod 16. And then I'm going to say that y has a remainder of 14. So it's going to be congruent to 14 mod 16. Okay, so that's the basic setup. Let's see what we can do. So for part A, find the remainder when their sum is divided with 16. So we want to do the sum. So add them together. X plus y. And we know that that is going to be congruent to the 11 plus the 14 because of our addition property. Now, we can just join that together. 11 and 14 is 25. And 25, when divided with 16, has a remainder of 9. So that's 9 mod 16. Pretty easy. However, part B is not so easy. For part A, let me just write x plus y is congruent to 9 mod 16. Part B involves a little bit of trickery. So, we want to find the remainder under mod 8 because we're dividing by 8 now. But we were dividing with 16. Now, something should immediately come to mind. The fact that 8 and 16, 8 is a divisor of 16. 8 times 2 is 16. So, let's rewrite the congruence statement for x. And the way I'm going to do that is like that fraction setup we have where we said that the difference of x and 11 over 16 is equal to an integer, k. That comes from the congruence statement we learned about. This is from a previous problem, where if two integers are congruent mod m, then their difference over m is equal to another integer, k. And what I'm going to do is multiply both sides by 16. The fraction over here cancels out. X minus 11 is equal to 16k. And I'm going to add 11 on both sides. And if you've been paying attention, this is just basically the division algorithm written out, where we know that x is sum value k times 16 with a remainder of 11. I'm going to have to rewrite that over here. X equals 16k plus 11. But I want to show... My game plan here is if I can show that x has some remainder when divided with 8, and then y after that has some remainder divided by 8, then I can add the two remainders together and get my answer. So how can I transform this equation into something divisible with 8? Well, the trickery I'm going to use here is the fact I know that 16 is divisible with 8. 11 isn't. And I need to get this to look like it's in terms of a multiple of 8. So what I'm going to do is I know 11 is 8 plus 3. So I'm going to put a plus 8 and a plus 3. Now I have a GCF with these two terms, 6k and 8. That GCF is, of course, 8. So we pull out the 8. We have 2k plus 1 plus 3. And now I have something in terms of 8. So if I kind of work in the reverse direction, subtracting 3 on both sides, reverse the process from what I did before, we have x minus 3 is congruent or equal to 8 times 2k plus 1. Divide by 8 on both sides, I get x minus 3 is equal over 8 is equal to 2k plus 1. And this right here is an integer. I know that because k is an integer. If k is an integer, 2k is an integer, because 2 times another integer has to be another integer. And if I add 1 to it, it's certainly not going to make that into like a decimal or non-integer. It's going to stay the same. So I have that the difference of x and 3 over 8 is equal to an integer, which means, of course, according to our definition, we have modulo congruence between a and b in the definition, or in this case, x and 3. So this establishes the fact that x is congruent to 3 mod 8. So that's crucial fact number 1. Now I must do the same thing but for y. So I know y, I'll do it in blue I guess, y is equal to, well again, I know y is congruent to 14 mod 16. So actually, not y is equal to, alright, I'll write it. Y is congruent to 14 mod 16. Which means that y minus 14 over 16 is equal to another integer, j. And let's just repeat that same process I did. So multiply by 16 on both sides. We have y minus 14 is equal to 16j. Because of course it cancels out the fraction. Add 14 on both sides. We get y is equal to 16j plus 14. I'm going to apply the same trick I just used. The fact that I can rewrite 14 in terms of 8. So y equals 16j plus 8 plus, well, 8 and 6 is 14, so plus 6. And then I factor out my 8. So 8 times 2j plus 1 plus 6. And then I'm going to skip a couple steps because I'm already using enough room as it is. But we will eventually get that the difference between y and 6 over 8 is equal to 2j plus 1. And again, 2j plus 1 is an integer for the same reasons that 2k plus 1 is an integer. So, and for the same reasons x is congruent to 3 mod 8, we have that y is congruent to 6 mod 8. So let's combine this fact and our fact over here. And now we can find the remainder of the sum. The remainder of the sum when divided by 8, which I'll do in red. So I want to find x plus y under mod 8, which I know is the same thing as x is congruent to 3 mod 8, and y is congruent to 6 mod 8. Therefore, we have that 3 and 6 is 9, and 9 is equivalent to 1 mod 8. So giving us our final answer of x plus y is congruent to 1 mod 8. So a bit of tricky logic, a bit of tricky arithmetic, but as we can see, we should always be looking for the connections. Well, we have a 16 and an 8. They're multiples of each other. Let's see and use what we know. I know that if the difference over 8 is equal to an integer, then I'll be able to find the remainder. Just use all the definitions and techniques that we have worked with so far.